we use what I call a sophisticated and yet elementary method to prove square root of 3 is irrational. Why do we say that? We're going to use some results with Diophantine approximation. The main result that we rely on is a characteristic of irrational numbers. We say that a real number x is irrational if and only if there exists a sequence of integers p sub n and q sub n such that the limit as n goes to infinity, this quantity goes to 0. That is, Pn over Qn is getting close to x. Now, of course, we assume Qnx minus Pn is not equal to 0 because otherwise the ratio of integer x would be irrational, right? So that's the result we're going to use. You may wonder, how do we find such sequence if I have an irrational number? For example, square root of 3. You can use continued fraction. In this case, 1, 2, 1, 2 will go on forever. It's going to be a periodic pattern here. Now, for easier notation, we can say we can truncate for the maybe nth part so that we can get a fraction Pn over Qn, right, with finite fraction here. For example, there's going to be a recurrence relation for Pn and Qn. If you plug in the numbers, we're going to get that. For example, if you go to the 13th iteration, and here this fraction is getting really close to true value of square root of 3. I think it's about right to either 7th or the 8th position after decimal. Okay, so here's the result. What is the proof? We're going to use this to prove that square root of 3 is irrational. Here we go. We consider this term. All right. If you're familiar with binomial theorem, you can expand it out. Notice that square root of 3 raised to a odd power is going to be some integer times square root of 3. If the even power is going to be some integer, right? That is, for this, after your expansion, you're going to get some integer p and q, right? So qn times square root of 3 minus pn. So when n equal to 1, 2, 3, so on and so forth, you're going to produce this sequence. We claim that this sequence here, the value here is going to go to 0. Why? Because square root of 3 we know is a quantity that is between 1 and 2. Square root of 3 minus 1 is between 0 and 1. For a number smaller than 1, if you raise to the nth power, it's getting smaller and smaller, and the n goes to infinity, the limit goes to 0. Okay, so that sequence satisfies this condition, and in the meantime, it cannot be 0 because why? Square root of 3 minus 1 is strictly greater than 0. If you raise to the nth power, it can never be 0. Okay, that satisfies the condition. Earlier, the theorem says that if there exists a sequence with this limit and not equal to 0 for all n, then x must be irrational. So here is the proof. Okay, of course, this is not complete until we prove the main results here, right? So the main result, we're going to rely on what is called the Dirichlet Approximation theorem. Here we say that for real number x and a given positive integer n, you can always find among those multiple of x so that some quantity is going to be getting close to some integer. The distance is at the most 1 over n. When n is big, this 1 over n is getting small, so you can have something really close to an integer. So what is the proof? We don't consider the fraction of those quantities here. Now this symbol here represents the fraction part of a number. For example, if I have 3.14 and this bracket will take 0.14, the fraction of the value here. So here, what we're considering this n plus 1 values, right? From 0 to either x or 2x or nx, the fraction part of it, right? Consider this fi. First, we claim that fi here always fall into interval 0, 1, right? 0 inclusive. That is, if you have a whole integer, the fraction would be 0, right? And the fraction can never be greater than 1. Now, we're going to subdivide this interval into n equal space intervals, each with the length 1 over n. right? So with n intervals, but we have n plus 1 quantities, we can use pigeonhole principle. Tells us that at least 2 of them fall into the same interval. If they fall into the same interval, then the distance is going to be less than 1 over n. That is, there exists I and j, so that this is true. We must have some integer p and some q, so that px minus q is getting really close, and then is less than 1 over n. The distance is less than 1 over n. Okay, that's the main results. Okay, go back and think about it. Try to prove it yourself. Now let's plug in some real numbers here. Let's say x is square root of 3, a real number, and let's n equal 10. All right, 1 over n would be 0.1. What we're saying here is that a multiple of square root of 3 must be close to some integer, and the distance is going to be less than 1 over 10, that is less than 0.1. All right, let's try that. Let's multiply 1, 2, 3 up to 10, right, of square root of 3. Here we go. We have 10 numbers here, and we split I equal to 4. Now 4x is 6.9, which is really close to integer 7, right? The distance is less than 0.1. All right, so that is 4 times this minus 7, less than 1 over 10. Now you divide it by 4, what we get is square root of 3 minus 7 over 4 is going to be less than this. So in other words, 7 over 4 is a good rational approximation of square root of 3 if we only care about the precision is under 1 over 10, right? Now we are ready to prove this theorem, right? How do we prove that? Now, if x is irrational, that part is easy, because if it is irrational, earlier the Dirichlet approximation is true for any real number, including irrational numbers. So we can always find this, right? This is by the theorem we just proved earlier. So which means, in this case, it can never be 0. Why? Because x is irrational. If this is 0, then x would be the ratio of 2 integers. That would be rational, right? So if x is irrational, we know that we can produce this sequence, and this quantity can never be 0. All right, that's a proof. Now, the theorem, remember, has if and only if. How to prove the if part? So if we can find integer sequence Pn and Qn with this condition, how do we claim x is irrational? We're going to prove by contradiction. Assume x is rational, right? That is s over t for some positive integer t, and then you do some simple algebra, you plug in here, and this quantity is ratio of 2 integers. Notice that we claim this is not 0 for every n. This cannot be 0, which means the numerator has to be at least 1. But the denominator here, t, is a constant. That is, this quantity must be greater or equal to 1 over t. All right? So this contradicts with the fact that the limit, and when n goes to infinity, is going to be 0, because this inequality here is true for every n. Right? If every n, and this is greater or equal to 1 over t, the limit cannot be 0. We have a contradiction, which means x cannot be rational and x has to be irrational. So we have proven the main results, and we use this result to prove that square root of 3 is irrational. That is why earlier I said the method is sophisticated, but still elementary, because that is based on some elementary results in number theory. Okay, hope you enjoyed this proof, and of course you like this video. I assume please like, share, and subscribe to the channel.